Okay, thank you. Yes. So I was very touched watching yesterday and today, many students struggling with the homework assignments. After, many years after the fact, you forget how non-trivial things were back when you were first learning them. So, and I also regret that I didn't quite get to, in my first lecture, to some facts that might have been very helpful for helping you do the exercises. But anyway, let's pick up slightly before I left off. I'll quickly review. We talked about two different ways to characterize massless spin 1 particles. First way of thinking about it was a pair of momentum and polarization vectors subject to p dot p equals epsilon dot p equals epsilon dot epsilon equals 0. I added something here that they didn't have last time. I forgot to include this last time, but I should have. Then we talked about the fact, so then I used Feynman rules to explain how to compute the n particle amplitude, which is defined for a collection of n ordered particles. Yeah. The ordering showed up because I only allowed myself to draw Feynman diagrams with the specific ordering of the particles, subject to one additional constraint, the momentum conservation constraint. Then I discussed the fact that thanks to this highly non-trivial property called gauge invariance, these amplitudes are actually almost completely independent of the choice of epsilon. So this is vastly more information than we need to specify, for all intents and purposes of studying amplitudes, we don't really need to specify all this information. So really one way to think about it is if this is the space, I mentioned this last time. If this is 2n copies of C13, and sitting inside it here is the submanifold subject to all of the constraints, star and double star. If I call these constraints here star for each particle, and this one double star, this is submanifold. And actually, here's the relevant point that I mentioned briefly at the end of last time. It splits into disconnected pieces. And the reason it splits into disconnected pieces is because of this quadratic constraint here. So for a given p, there are two different branches of solutions. So this space has 2 to the n disconnected components. And when you use Feynman diagrams to compute this, you get a formula that's very, very complicated in general, but it's simultaneously valid in all of these disconnected components. Then I described how we switch to spinor helicity variables. Where we have two spinors called lambda and lambda tilde, and a choice of helicity h equals plus or minus 1. And if we have n particles and we specify a choice for each one of these n particles, then we're saying that we're picking a particular component inside this kinematic space. So what we do then is we define the helicity amplitude and it's conventionally written like this. Oops. Epsilon plus. Okay, I wrote this formula last time. I'm just reviewing it. Oops. And here the point is that the choice of R tilde is irrelevant. Okay, so I've written a lot on the board. Let me go back and review. We define a helicity amplitude to be a formula that's valid in one of these particular patches, where we make a specific choice, either epsilon plus or epsilon minus for each one of the n particles. That's like choosing a particular branch of solutions to this quadratic equation that we live on. And thanks to gauge invariance, it's sufficient to choose a particular representative solution. And if you switch to a different solution, a different choice of polarization vector, you'd just be moving around within the space where the amplitude changes by no more than rescaling by an overall factor. Right. The normalization constants here are chosen so that epsilon plus dot epsilon minus is equal to -1. So we partially fixed that overall scaling freedom. Okay. Anyway, this is just reviewing where we were at the end of last time. And as those of you who are doing the exercises may have noticed, you're free to choose n different reference spinners here if you want, if it's helpful to do so. So this defines what the helicity amplitudes are. And then I'm going to give the answers to some of the exercises. Although, as I said at the beginning, even the simplest of these can be somewhat non-trivial calculations. Let's look at the n equals 3 helicity amplitudes. Okay. There are sort of two prototypical amplitudes. Okay, and I just quickly remind you about the notation. These brackets denote determinants of the spinor variables which we think of as column, row or column matrices, just by convention. And these are 0. And here, these amplitudes have two obvious permutations. So notice here that particle 1 is special because it's the one with positive helicity. But if you wanted a similar configuration, let's say you wanted minus plus minus, you can just take this formula and cycle to move the plus onto the 1. So I'm just going to write, rather than writing all the formulas, I'm going to write and two similar cyclic formulas, and also here two similar cyclic.
And the formulas you're showing are what we would get from the unique Feynman diagram?
Yes, exactly. So in this case, there's a unique Feynman diagram that looks like this. So it's essentially up to a factor of minus I. It's what I called V3 from last lecture. To be precise, I even have it written out here. It's minus I. It's minus I V3, which if you work it out, comes to 1 over root 2 epsilon 1 dot epsilon 2 times epsilon 3 dot P1 minus P2 plus 6. Okay, so the first exercise on the exercise sheet, right? So for n equals 3, this is the unique Feynman diagram. And the exercise on the exercise sheet was to calculate the 8. There are 2 to the third, which is 8 different helicity amplitudes. Here are the 8 answers. 3 plus 3 plus 1 plus 1 is 8. And you get these formulas by taking these expressions and plugging them in here. Although again, it's not completely obvious, and it requires several manipulations. Are there any questions about this point before I move on? Okay. And for those of you who've reached your wit's end, if you go to the paper whose archive number I gave at the beginning of my first lecture, there are some more details spelled out about how to do these calculations. Okay, so it turns out that spinor helicity variables give shockingly simple formulas compared to the P and epsilon form. And the prototype of this, so for example, if all H's are the same. So this is a fact that's not immediately obvious from Feynman diagrams. You can prove it. You can prove it in a couple of different ways. But I'm just stating it here as a fact. Or if all but one of the HI are equal. So the first interesting case, the first sort of marginal marginally non-zero case is what we call MHD. That word stands for maximally helicity violating. And let's take the example when all of the particles have positive helicity except for I and J. So all have helicity +1 except for I and J. And the result for this amplitude is given by a famous formula called the Park-Taylor formula. Actually, and we saw this yesterday in one of the we saw essentially this formula yesterday in one of the Zoom talks in a context that I confess I didn't understand. But it just shows how ubiquitous this kind of thing is. Downstairs, we have the cyclic product of all the adjacent angle brackets that cycles back to itself. Okay, again, I'm certainly not proving this is true. I'm just mentioning that one of the virtues of working not with the full amplitude, but with these helicity amplitudes, they're specifically tuned to look at individual, regions in this kinematic space, is that you sometimes get these spectacularly simple formulas.
So Mark, if
Yeah.
N equals 3 special then, because I mean, this would mean that they would all be 0 for N equals 3, all but one. All right.
Yes, yeah, thank you, yes, thank you, yeah, that's important. There's something very special happens for N equals 3. Except N equals 3, thank you. N equals 3 is a degenerate case where you do have these two formulas. And the reason that it's degenerate is that it just, if you look at the 3-particle kinematics, this is worth stating. But I need to delete it. Are there any questions about this before I delete it? Yeah.
There's just a typo in the first formula.
Yes, there is a typo. You should have called me out earlier. Yeah, that should be 3-1. Thank you. Okay. Yeah, I'll just mention this briefly because it is an important point. For N equals 3, the requirement that P1 dot P1 is equal to 0, and P2 dot P2 is equal to 0, and P3 dot P3 is equal to 0, and P1 plus P2 plus P3 is equal to 0. Oops. These all together imply that actually Pi dot Pj equal to 0 for all I and j. The way to see that is like, suppose you take the dot product of this with the equation with P1, and then the dot product with P2, and then the dot product with P3, and you'll see that the only solution is that all of these inner products are equal to 0. And then when you translate that to spinor helicity variables, that implies that Ij times Ij is equal to 0 for all I and j. And so 3-particle kinematics requires either that all ij are equal to 0, or all ij are equal to 0. So that's a very special degenerate case. So the formulas that I had written previously, like I had this formula, there's an implicit, this is true in the case where all angle brackets are equal to 0. Because this formula wouldn't make sense in the case where these brackets in the denominator were 0. Are there any other questions? Thank you. Okay. Non-MHV amplitudes these are much more complicated. Okay. We call an amplitude NK MHV. This N stands for next to if it has K plus 2 H felicities -1 and N minus K minus 2 HI equals +1. Okay, now I want to give an example here. I'm actually going to write this whole thing on the board, just so you get a feeling for what these look like. This is on the example sheet. The simplest, or an example of an N MHV amplitude, helicity amplitude, is this one, the 6-particle amplitude with 3 negative felicities. This is a sum, well, the most compact way of writing it is as a sum of 2 terms. Now there's a little bit of notation here that I'm going to define in a second. You don't want to write this out. You don't need to, it's on the exercise sheet. Okay. Now there are 2 new notations defined there, or used there, that I now want to quickly define. A, B, C, D defined as AB, BD plus AC, CD, and S, ABC. This is it. It's defined as PA plus QB plus PC squared, and that's with respect to the Minkowski dot product. And this is proportional to up to a factor of 2 or minus 2, depending on your conventions. AB plus AC plus BC. I'm going to spend several minutes discussing various aspects of this formula, but are there any questions about it? Yes.
Like you were using square brackets for like row and like the angle brackets for column.
Yeah.
Here like B and like they can all be rows and column. Like why do we need two notations for the determinant?
Oh, yeah, that's okay. Good question. And actually, this is a great opportunity for me to mention, yeah, something very important. If you look back at these formulas, thank you. Okay, good. So this is an aside that I should have mentioned earlier. This is a crucial point. Note that under a rescaling, lambda goes to lambda times z, and lambda tilde goes to lambda tilde time divided by z, for z being any non-zero complex number. P is unchanged. Obviously, okay, so we've introduced these new variables in order to parameterize our space of momenta, and they're over complete. There's a redundancy. But now let's ask ourselves the question: how does this redundancy act on our choice of polarization vectors? But epsilon rescales as epsilon plus or minus goes to epsilon plus or minus times z to the power minus 2h. You see, because if I choose this is for h equals plus 1, and this is for h equals minus 1. So if I choose plus here, my lambda tilde gets a factor of 1 over z, and then the denominator here I get a factor of z. So altogether I get 1 over z squared. And here I get 2 factors of z in the numerator. Okay, so one of the reasons why it's useful notationally to distinguish the lambdas and the lambda tildes, so you can, it's just useful so you can look at a formula quickly by eye and check this rescaling. Let's take this formula and see if it makes sense. Like, in other words, I'm going to tell you right away that I will be able to know there's a typo here if I put a 3 there. Okay, and the way I do it is the follows. Let's imagine, now you're allowed to do this rescaling separately for each particle. So let's look at this formula and let's take lambda 1 and rescale it by z. And let's look at the right-hand side and see how everything scales. Here I've got one factor of 1 in the denominator and 2 in the numerator. So this term will scale as z squared. And here, where is 1 appearing? Well, I've got 2 powers of 1 over z in the denominator. That's 1 power of z in the numerator. This thing, if it's inside here, has no net scaling. Because so with the b and the c, the ones inside this interior here, there's no net scaling, and also here, there's no net scaling. So here there's no net scaling, and here there's no net scaling. So altogether, this term is also z squared. And that's consistent with the fact that particle 1 has negative helicity. So you see, if I made an error and put a 3 here, I would be able to catch my error by checking the rescaling of particle number 3. Because now, if I count the powers of z, I have z cubed in the numerator here, and 1 over z, 1 over z. That would be z to the 5th, so I know there's a mistake. That's why notationally, it's convenient to maintain a different notation for the determinants of the lambdas and the lambda tildes. So thank you for offering me the opportunity to give an answer that I hope answered your question, but also went much further. So for those of you who are doing the exercises, check your work at intermediate steps. So for, yeah. All right. Good, yeah, this rescaling, of course, will become crucial when we connect this all to projective space and Grassmannia. Oh, I'm sorry, and I forgot to mention, the reason this works, I remind you again, as was evident from yesterday's lecture, that every amplitude is by construction linear separately in the polarization vector of every particle. That's why this whole thing. I'll restore that. Correct. Okay. This formula exhibits what we call spurious poles. So there's a principle in physics called locality, which has been mentioned in at least 2 of the lectures so far. For my purpose, locality means that amplitudes can only have simple poles, never double poles, and only at locations where so here's a combination you've seen in several lectures where some cyclically adjacent momenta become null. Okay, so for example, P2 plus P3 squared is proportional to, again, there's a factor of 2 or minus 2 depending on conventions. It's proportional to this product, 2, 3, 2, 3. So these kinds of things are all allowed poles. Anything you have, and 6 and 1 are adjacent because everything is cyclic. These are, oops, that was a mistake. It's too eager. These are perfectly allowed by locality. These poles are also allowed by locality because S234 is just P2 plus P3 plus P4 squared. But here, these factors in the denominator are disallowed. They indicate the presence of what we call spurious poles. So exercise number 3 asks you to show that the residue of this, the sum of these 2 terms is actually 0 if you try to approach a location where this thing goes to 0. So in other words, it's a sum of 2 terms and the residues of the 2 terms at that pole add up to 0. Any questions about that? So it's a very common feature. Let me emphasize that in the Feynman diagram expansion, this was completely manifest because there was only one place in my Feynman diagram discussion where I had any denominator at all. And that was anytime I have an internal edge E, there was an explicit factor of 1 over PE dot PE in my definition of the Feynman diagrams. And because I used momentum conservation to determine these PEs, it's clear that, you know, if you have some collection of particles here, I plus 1, I plus 2, up to I plus j minus 1, it's clear that the momentum flowing through that edge is going to be, that sum. So from the Feynman diagram point of view, it's manifest that you only have these poles. But from the more compact expressions we get from these more sophisticated methods, these spurious poles are ubiquitous. They're unavoidable if we want to have more compact expressions. And this also allows me to segue nicely into the other physics word that you've heard a lot about. Unitarity is the statement that the residue of an amplitude on any pole is a product of lower point amplitudes. So fortunately, I still have this picture here. If I wanted to know if this was one of the Feynman diagrams contributing to some n particle amplitude, and I wanted to know what is the residue of that amplitude on some pole of this form, first of all, I would take the subset of all Feynman diagrams that have this propagator. And we typically denote that by, like, suppose this is an n particle amplitude. You sort of fill this in with a blob. And we fill this in with a blob. And that notation means all Feynman diagrams that can have anything going on here and anything going on there, but contain this edge. Because Feynman diagrams that don't contain that edge don't have this pole, so they contribute 0 to the residue. And so to finish my sentence there, the residue becomes the sum of all Feynman diagrams of this type, you know, with this excised, and that just gives you the product of this amplitude times the product of this amplitude. So that's the statement of unitarity. Are there any questions about that? That's the general idea. Maybe I haven't explained it in full detail, but that's the point. Okay. All right. I think the last thing I want to say about this formula is, where do these formulas come from? So in physics, we have something called the BCFW recursion at Sanford, Brito, Cacciazzo, Fang, and Witten that allows you to recursively compute any n particle helicity amplitude . in terms of smaller amplitudes. And the seed for the recursion are the n equals 3 particle amplitudes I summarized. Okay. I won't say more about the BCFW recursion relation. It's beautiful, it's simple. You can teach yourself how to do it. You can teach yourself how to compute this recursively by splitting it into 5 particle, then 4 particle, then 3 particle amplitudes. But because I want to get onto the amplituhedron, I just wanted to mention that there is a known and relatively simple algorithm for generating formulas of this type, but they will all be afflicted by spurious poles. Are there any questions at this point? All right. Now I'm not going to write, actually, I said that's the last thing I wanted to say about this formula. No, there's one more. Exercise 4 asks you to show that this formula is equivalent to a different one that is a sum of 3 terms that lacks the 2, 3, 4, 5 pole, but has 3 other spurious poles. So first of all, for the amplituhedron experts who thought that the 6 particle NMHV amplitude should always be a sum of 3 terms, it's just because in this particular helicity configuration, for reasons that I'll get to in a minute, it's kind of a degenerate case and one of the terms goes to 0. So there's another formula that I don't have time to write on the board, but it's on the formula sheet. It's exactly equal to this one, but in a highly non-trivial way. And it doesn't have this pole at all. So, one way to prove that that is not a pole is to find another formula where you don't even see that in the denominator at all. But that other formula has 3 different spurious poles. So the existence of different formulas for the same thing was really the thing that led Andrew Hodges in his groundbreaking 2009 paper to the idea that maybe the way to interpret what's going on here is that these formulas are calculating the volume of something in 2 different ways by triangulating, you got some space and you triangulate it in 2 different ways. One way you cut it into 2 pieces and you get these 2 terms, and a different way you cut it into 3 pieces and get 3 different terms. And these spurious poles arise from, like spurious edges or facets where you glue together 2 of the pieces. So I'm intentionally using language that closely mirrors language used in other lecturers, because that's the whole point, because we're all describing the same thing. But sort of historically, it was Andrew Hodges' observation that based on formulas like these, that ultimately led to the amplituhedron, which is where I'm going next. Okay.
Is there a geometric interpretation of this?
Yeah. I mean, these are volumes of a cyclic polytope. But it's a little bit.
Yeah, I guess.
Sorry, it's a little.
To the one with the 3.
Yeah, you're used to the one with 3. Yeah, it's slightly different than your way of thinking about it, but it's there explained in. Yeah, so I should not use the word cyclic polytope. There's a polytope, and it's explained in Hodges' 2009 paper.
This is the net 3, right?
Yeah, it's not right. Yeah, because we're in. I haven't introduced. Yeah, it's in,
Okay.
his polyfill is in P3, not in P4. As this little side discussion has indicated, there's one more change of variables I need to do. Before we really get to the heart of the modern formulation of the amplituhedron. I want to introduce a third way to parameterize kinematic space. And that is momentum twistors. Okay. So the claim is that there is a bijection between generic. That's a key word that I won't write the exact criterion for what it means, but I think you'll understand what I mean when I'm done. Configurations of n ordered subject to momentum conservation so we're going to use I'll use homogeneous coordinates Zi, I runs from 1 to n on P3. Okay, so each Zi is a 4-component complex object. And I'll use the notation, the obvious Plücker notation, where IJKL means determinant of Zi, Zj, Zk, Vl. And now, so generic means, it means several things, but among other things, it means that I plus 1, I plus 2, I plus 3 is not equal to 0 for all I. So you don't want, yeah, I think this is the usual way in which mathematicians use the word generic. You don't want to accidentally have 4 cyclically consecutive points accidentally being coplanar. But it also means you don't want any degeneracies in your spinor helicity variables either. So the idea is just for generic kinematics, away from certain special loci, there's a bijection between configurations of n-ordered particles subject to momentum conservations and configurations of n-ordered points. This is very useful in part because notice that these are completely unconstrained. Whereas here we have this rather awkward quadratic constraint. So those of you who are working on the exercises know that sometimes you struggle to prove that 2 things are equal because they're only going to be equal on the locus of this quadratic constraint. And often it's hard to sort of see how to use that constraint to get from one formula to another. Whereas when you switch to these momentum twister variables, they're completely unconstrained, which is a nice advantage. So let me just give a brief formula for what they are, how to define them. Now, the flip side of that is that when I switched from momenta and polarization vector to spinor helicities, it was a one particle at a time. But here, when I switch to momentum twisters, it applies only to the full collection of particles. I'm going till 12:10, is that right? That's right. Okay, so 10 minutes. Okay, the formula is the follows. Here I put the two component spinor helicity, and then I define this. This is a beautiful geometric interpretation, but for lack of time, I won't really have time to do justice to it. Here you see, I didn't give a full definition of generic because when I defined spinor variables, I required this pair to be a non-zero element of C2. But if you're coming from the point of view of projective space, you'd be, 0, 0, 0, 1 is a perfectly fine point in projective space. It's just outside the region of validity of this direct transformation. So again, I'm just emphasizing that this is all for generic kinematics. Okay, that's the definition of momentum twisters. Now, we assemble the N momentum twisters into a 4 by N matrix. And where I want to go, I want to be able to say that our amplitudes are functions only on the Grassmannian 4, n. Now there's a huge leap there, because in order to say that something is well defined on the Grassmannian, I need it to be, depend only on the vector space that the rows of this matrix span. In other words, I need the thing I'm describing to be invariant under GL4 transformations acting on the left that change the row span. Now, what happens is if you unpack what happens if you do a generic GL4 transformation on your momentum twisters, it does something really remarkable. It mixes the different spinor helicity amplitudes amongst themselves. There's my eraser. So the last ingredient we need before we can make a direct connection to the amplituhedron is we need a bookkeeping device. We need a bookkeeping device to assemble various combinations of helicity amplitudes into GL4 invariant combinations which then will be well defined, at least on an open set on the Grassmannian. I mean, it'll be a rational function, so it'll have poles, of course. But at least the whole notion of calling it a function on the Grassmannian will make sense. So are there any questions about that goal? So here's how it works in practice. We need to introduce Grassmann variables. So I'll just review the definition of this and then I'll quit. So Grassmann variables are defined by the fact that they anti-commute. And consequently, each one squares to 0. So if you have a function of a Grassmann variable, it has a Taylor series expansion that terminates after the first order because there's no plus order theta squared term. And if you have a function of n Grassmann variables, it has an expansion with 2 to the n terms. And the last thing I need to define before we end is the notion of Grassmann integration. So let me pause. This is not, don't think that this is super exotic. Because the way you should think about this is a way of encapsulating two pieces of information. Like if these are functions of some other ordinary variable, let's call it x, then what you're doing is you're encoding two different functions, f0 of x and f1 of x, into a single object. And that provides certain bookkeeping efficiencies that, amongst other things, will let us construct these GL4 invariant combinations. So to finish my thought here, Grassmann integration is defined as and extended by linearity. So therefore, integral of f of theta d theta is equal to what I called f0 before, which is equal to f of theta evaluated at theta equals 0. Those are all the same thing. And the integral of f of theta theta d theta is equal to what I called f1 before, which is df by d theta evaluated at theta equals 0. Because when you plug, I'm sorry. Whoa, no. I have it exactly backwards. Wait a second. Yeah,
Just F0, F1.
yeah, sorry, yeah. Yeah, okay, good. If I plug this in here, this should be, I have it backwards, right? Yeah. Because if I plug f of theta into the first expression, only this term survives and gives me f1. Whereas if I plug f of theta into the second expression, this term is killed because theta squared is equal to 0, and I just get f0. Okay, yeah, that's correct now. Okay, so I'll end here, and then after lunch, we'll use this bookkeeping device to assemble different helicity amplitudes into very nice packages that will connect to the amplitude heaters.